Good morning, everyone. Welcome to IME 470 class. Today is May the 1st. And first of all, let me share my screen and also stop my video. Okay, so first of all, in the last class, we've mentioned what it is. We've mentioned the formulation of this one. Remember it? We had the problem of MFP2, and we want to formulate the dual of the MFP2 to see what does it look like. And so this is the example. Okay, so this is the example for the last class. Actually, it was for this network, remember it? So first of all, we solved the MFP, the maximum flow problem. For this one, we've modeled the maximum flow problem for this one. Then we denote, the corresponding variable for the first variable. The corresponding variable for the first constraint. Where it is? It's here. We define this one to be ZS, and the variable corresponding to the second constraint, which is to T, to be ZT. And then this is the intermediate variable for node 1, defined by Z1, for node 2, Z2, node 3, Z3, node 4, Z4. And the flow capacity variables, flow capacity constraints, we defined the corresponding one to be YST. And then we write the dual form of that LP to be this one, see it? And we have found that this one is what? Is nothing but what? But the MCP. See here? MCP2 actually. You can clearly see, let me make it smaller. So let me see. So this is the MCP2. And this is the formulation that we got. See it? They are the same actually. Or let's make it even more explicit. You can compare these two. See it? Of course, I changed the order of this one. I moved this one to be the first constraint, which is this one. And all others are exactly the same. You see it? Of course, I write it to be Yij minus, for example, Ys1 minus Zs plus Z1 greater than or equal to 1, for example, here, which is here, can be found here. So, and all others are the same, see? And be careful that this is the first type of formulation of MCP in which I have both Zi and Yij's are what? Are binary variables. But actually in formulation 2, which is here, you can clearly see that they're equivalent. The formulations of the minimum cut problem, MCP1 is equivalent to MCP2, in which I have what? I have Zi, Yi's are continuous variables. Both of them are greater than or equals to 0. Instead of, previously we say they must be either 0 or 1. Here, theoretically, I would allow you to have Z equals 0.5, for example, Yij equals to 0.6, for example. However, due to the total unimodularity, a property that I mentioned in one of the homework, which homework? Homework 4 or 5, I think, one of them. Due to that, so that you will not have a solution between 0 and 1. You must, final solution would be either 0 or 1. In other words, this continuous problem is completely equivalent to what? To this minimum cut problem, okay, to this binary problem. Then again, you may ask a question, say, hey, you've already formulated by a binary program, why you want to make it to be continuous? The reasons, again, in general, for a continuous problem, to solve a continuous problem is much, not a little easier, much easier than solving an integer program. In general, an integer program to handle, let's say, a relatively dense network. By saying dense network, what I mean is, for example, the network, the graph, exists for many xij's for any pairs of ij. The worst case is, for example, consider a complete graph. Complete graph means that for any nodes in the graph ij, I will have a pair, ij pair. So, for example, a complete graph. Okay, so for example, you can have a look at this. Here, how many nodes do I have? I have 1, 2, 3, 4, 5, 6, 7 nodes, right? So complete graph means for any two pairs, there exists an edge or a arc. So this, in this case, it is a densest. When in this case, to solve, a graph, let's say with only about 50 to 60 nodes, I mean, if you brutally solve a node, this kind of problems, this kind of NP hard problems, I should say, then it's gonna be stuck. In other words, use our regular computer, even a graph with only 6 to 7 nodes and with some modernist solver, it's gonna be stuck. You believe it. And for many days you solve, I don't think you can get the answer. Running continuously, 24 hours for many, many days. Then it's gonna be a problem. However, if you formulate it as a linear program, then even if you have how many, say even if you have millions of this kind of variables, use our regular computer, I'm almost sure in most cases within 1 or 2 hours, you're gonna solve the LP. That's it. Even millions of variables. So for example, as we just mentioned, for a complete graph, suppose I have, for example, n nodes. So how many graphs, how many edges do I have? I should have O(n) squared. If I want to say it accurately, it should be n choose 2, which equals n times n minus 1 divided by 2. That's accurately, but usually you can say it's about n squared. Get to the highest order of the polynomial of x. So that's the case. That's the reason why we want to, if it's possible, we always want to have a linear program to describe a problem instead of an integer program. Of course, in most cases, you don't have any choice. You must use integer program. But luckily, that in MFP and in MCP, we do have. We can formulate them to be linear programs instead of integer programs. Okay, and so here we've already seen for this specific graph, the MCP2, sorry, the MFP2, the dual of it is actually MCP2. Now let's have a look at the general case. By the way, so as we've already discussed in the previous lecture, if a problem is what? If a problem is, let's say if LP1's dual LP is LP2, then we have showed that LP2's dual must be LP1. Remember, it's a homework problem that I asked you to do. Homework 3 or 4, I forgot. One of the homework, let me see. Operations research homework 4, I guess. Let me see what is homework 4. Yes, here we go. Suppose a primal LP is this. We know the dual is this one. Proof that the dual of this LP is a primal. See it? So because of this, so I don't have to formulate the dual of this one again. Why? Because this dual must be the primal, which is this one. Okay. So now let's do the same thing for which problem? Let's do the same thing for the general case. That we know the general maximum flow problem use MFP2. Where's MFP? Using MFP2, here we go. I want to find the dual problem of this problem, the dual LP of this problem. And let's see whether it's really the MCP2 as we already claimed. Let's see it. So first of all, I write it too big. Let's consider this part first. So this is what? This is the MFP2. See it? The only difference is that I move everything to be something minus something less than or equal to 0. So why did I do it? The same way as what I did here, remember? I also made it to be something is less than or equal to 0. The reason is because in this case, I can really formulate the dual problem. Otherwise, I cannot directly formulate the dual problem. Why? Because here, lecture 7, I think, duality, right? Because here I have what? Here I have this, the table, see it? I need to make sure that everything with respect to x is in the left-hand side. And the right-hand side is only what? It's only a constant. For example, 0, or for example, whatever number. The right-hand side should be only a constant. And that's the reason why I want to move this one in this way, because in this case, the right-hand side will be only a constant. If you, for example, write in this way, you see, the right-hand side is not a constant. It's still related with this kind of axis, let's say xj, x0, That's the reason why I want to write, in that way. Okay, so let's start from this formulation to see what is its dual. First of all, I denote this constraint, which is the constraint with respect to x0 to be zs. The second constraint, which is also with respect, I should say this. This is with respect to node S. Remember, what does this mean? This constraint mean? This constraint simply means the total entering is less than or equal to x0. So this is related with node S. How about the second constraint? The second constraint means that the total, the first constraint means that the total flow should be greater than or equal to S, not less than or equal to. If you move it to that side, then you're going to have XS, X0 is less than or equal to that part. So the total flow must be greater than or equals to X0. And the second constraint means the total flow must be less than or equal to X0. And this is clearly for node T because of this. Here you can see T is fixed for any I which can reach T, which is actually the in neighbor of node T, summation of xit is less than or equal to x0. So I denote it to be zt. And here I do what? This is for each intermediate node I, see it? Because here I is fixed. This is for any j in neighbor equal to, or here is less than or equal to the out neighbor. So this I denoted to be zi. See, exactly the same as here. This is with respect to node S. I denoted it to be ZS. This is with respect to ZT. I denote with node T, and I denote it to ZT. All these are what? All these are intermediate nodes of nodes 1, 2, 3, 4. So I denote them correspondingly by Z1, Z2, Z3, and Z4. And finally, what do I have? Finally, I have the capacity constraint. See it? For the capacity constraint, for each yij, for each ij in A, I have defined it to be one ij. Okay, so after setting these kind of variable notations, let's write the dual to see whether it's correct. First of all is what? First of all is the objective function. So I have a maximum problem in MFP2. So the corresponding dual, let's forget about the MCP. Let's just consider the dual. I must have a min problem. See it? And the constraints will, the variables will be what? Will be zi's and yij's. See here? Okay. And then how to write the right-hand side, how to write the objective function in the dual problem. You're going to summation of the right-hand side, right? Which means you're going to have 0 times zs plus 0 times zt plus 0 times zi for any I, summation of 0 times zi. And for any ij, you will have what? Cij, sigma Cij times Yj. And all these zeros are gone. See, here I have 0, 0, 0, nothing here. But I do have a Cij, Yj here. And that's the reason why your dual objective function is going to be min of sigma ij in A, Yij, Cij, Cij, Yj. Okay. And then let's have a look at the second thing, which is all these kind of what? All these kind of decision variables. What should the decision variables mean? What should the decision variables be? Again, for decision variables, you need to see what? For decision variable, here, it means, for example, let me first clear everything here. For decision variable here, for example, xij, sorry, for example, x0. X0 means what? Means a corresponding constraint in the dual, right? Remember, again, a primal decision variable means a dual constraint. A primal constraint, for example, a primal constraint here means a decision variable in the dual. A primal variable means a decision constraint in the dual, right? A primal variable means a constraint in the dual, and the primal constraint means a decision variable in the dual. So here, for x0, let's find where do we have x0. We do have x0 here, which is 1 times x0, we do have x0 here, which is -1 times x0. Can you find x0 in another constraint? Clearly you cannot. Here everything is xij. Here everything is xij. So I only have x0 here and here. So that correspondingly, what do we have? We have a 1 times zs minus 1 times zt is greater than or equal to 1 here. See, because here, the objective function here is 1. Remember how you formulate the dual? Let's go back here. See here? The prima is this one. So have a look at here. You have what? You have your type of constraints is something like this way, see it? And your corresponding dual variable, sorry, it's here. Your primal variable is in this way, xij is greater than or equal to 0. And this is standard to standard, see it? Your dual constraint would be what? The summation of this one greater than or equal to Cij. This Cij means what? The coefficient in the primal objective function. The coefficient in the primal objective function with respect to x0 is 1. See it? And hence you have this one. 1 times this minus this 1 times zt is greater than or equal to the objective function coefficient of x0 here, which is 1. Okay? Now let's have a look at the second variable, which is xij. So here is for any ij in A. Let's fix it for a specific I for a specific j. Where can you find it? First of all, you can find it here, xij here. See it? And this is a negative sign here, okay, corresponding to zi. So you will have a -1 times zi. Okay, the second xij you can find here. See it? Xij is less than or equal to Cij. The corresponding dual variable is Yij. So that you will have a positive 1 times Yij. Can you find another Xij? The truth is yes. It's actually from here. Then you may argue, hey, this is Ji, not Ij. Why you claim this to be Ij? The reason is because consider what if for Zj. If the corresponding variable is Zj, what do you have? Okay, let me explicitly write it down. Then I guess it's going to be more clear. Let me explicitly write it down. So if I'm considering here, let me make it in this way. Okay. Suppose I'm considering. Wait a minute. Why it's so big? Okay, let me make it. Let me adjust the format a little bit because I want them to be the same. Layout. This is fine. Okay, I see the point. Maybe because of this. Okay, here we go. Great. So let's have a look. Now let me explicitly write the corresponding constraint for Zj, which is for node j rather than for node I. So for node j, you will have what? Specifically for this, let me write in this way. Let's say, okay, let me specify this j. In other words, this j is fixed. For example, j equal to 5, whatever you want. So here I would have I ij xij minus here's also I ji xji. So what I did here was just to flip j and I. See it? Why? Because here I is fixed, while j is not fixed. But here my j is fixed, I is not fixed. So you can see wherever I have j, I wrote it here as I, and wherever I wrote it as j here. And you get a point here. See where you get another xij? It's here. So you have an xij here with the corresponding dual variable to be zj. You have an xij here, negative xij here, with the corresponding dual variable to be zi. You have an xij here with the corresponding dual variable to be yij. So what do you have? You have 1 times yij plus minus 1 times zi plus 1 times zj, isn't it? And then we have what? And then we have this, see it? Have the first constraint and the second constraint. Why it's versus 0? Because can you see what is the coefficient of xij in your primal objective function? 0. So the right-hand side is 0. And why this is greater than or equal to? Because it's standard to standard. Why? Because have a look at here. Your xij is greater than or equal to 0. So it's standard. So the corresponding constraint sign should be standard as well. And because this is the main problem, the standard is greater than or equals to. And hence, you must have yij minus zi plus zj is greater than or equal to 0. See it? And then how about the decision variable, the signs of decision variables in the dual problem? Remember what you do? You're going to have a look at what? The constraint, right? The primal constraint. Okay, let's have a look at the zi first. Your constraint sign is what? As less than or equal to. And your primal problem is what? Is maximum. So maximum versus maximum less than or equal to, it is what? It is standard. Standard to standard. So your zi variable here should be greater than or equal to 0. And the same for yij. Yij is also less than or equal to, so standard to standard. My yij is greater than or equal to 0. And then have a look at this problem. What is this problem actually? This is exactly, this is actually exactly MCP2. Let's see here. See here? They are exactly the same. Of course, again, I changed the order. I mean, I wrote this one to be the first constraint, and all others are exactly the same. See it? Wait 1 minute. Strictly, I should write something here. Strictly, I should write something here, which is for all ij in A, because I do this ij for all for all these ij is in A's. For any fixed ij, I can write it in this way, and of course I can do it for any edges, so that I have for all ij, any arcs, so that I have for all ij in A. Any questions about this part? For the dual variable here, as I just wrote, you need to write it by yourself after the class, practice it. You know, first of all, reformulate this problem, which is an explicit, you know, a detailed example, which is, you know, more intuitive. It's not kind of like as abstract as the example that I just finished. So rewrite the dual LP of this problem by yourself and verify it is the same as this one, okay? And after it, what you need to do is try to write this, the dual, the dual LP of this problem, which is MFP2, as what I did here, and I try to write it to be this problem, to get this problem, MCP2. And as an exercise, you can do this. Suppose this is a dual problem, this is a primal problem, which is MCP2, try to write the dual, and you should get this, the MFP2. And correspondingly do the same for an abstract problem, which is you start from this problem, the MCP2, try to get a dual, and you should be able to get MFP2. And after doing all this, I think you're gonna understand the maximum problem, maximum flow problem, and the minimum cut problem, plus the LP duality reformulation very well. Any questions? No question? Okay. Now let's have a brief review of the contents that we learned in the whole semester. Let me see. Here is a summary that I wrote. I actually summarized it yesterday. Let me see. I will upload this document to the Blackboard, no worry. First of all, I want to mention is, let me go to the Blackboard. First of all, what I want to mention is that all the assignments and the corresponding solutions are here. That is what I mentioned in the very first and the very second class of of the course in this semester. All solutions are here, okay? If you are not sure about some answers, or if you see you got some points, let's say, taken in your homework, you'd better check the solutions. And sometimes in many solutions, I remember I had a lot of comments. For example, here, no comment. Okay, so it's number 3. Some problems I have some comments there. These comments are, where, give me a second. I remember I have a comment in, oh, no, Excel, no, it's homework 5, I think, yes. Homework 6, I cannot show you the answer so far. Okay, so from here is something about total unimodularity, which is actually a very important, super important part connecting the integer program and the linear program. If you're interested, read this part. And here you're gonna see a lot of beautiful tricks. By these kind of beautiful tricks, will make our tools like the Garmin. You know, the Garmin is a GPS. You know, before we have Google Map, Yahoo Map. Before it, everybody was using Garmin. Till now, let's say if you're interested in this kind of sailing, say you play the sailboat. I don't know how many of you want to conquer the Atlantic or the Pacific, for example. Then probably you want to play a sailboat. In this kind of navigations, a sailing boat or this kind of sea navigations, till now we are using Garmin. Okay, Garmin is a very famous brand name. And why we can make this kind of shortest path, or let's say the ways from A to B, very fast, because of total unimodularity of the shortest path problem. If we don't have it, trust me, even if you just calculate from Walmart to NDSU, it's gonna take you huge amounts of time and you cannot tolerate it. It's gonna take a great inconvenience into our life. So think about this. It's very interesting because this thing was already finished, you know, many decades ago. But who knows tomorrow? If you have a look at more and more these kind of problems tomorrow, you may be the creator of another powerful tool, and that's going to greatly benefit our generations. It's great, and that's really the contribution of the life of, you know, to the society, to the community, and also kind of like a meaning of the life. Anyway, that's just my personal view. Now let's have a look at the review part. So I need to correspondingly open the lecture notes to make it more clear. First of all, in lecture 1 and also lecture 8, I believe, in lecture 1 and lecture 8, we mentioned something, excuse me, we mentioned something about the formulation, the models, okay? And we have linear models, we have integer models, and the nonlinear models. So in the exam, it's possible I ask you to formulate a model. You know, here, lecture 8 is mainly for integer, modeling with integer variables. And also, remember, we had a homework. So it's very important for modeling, because as we mentioned in the class, that finally, let's say if you have already formulated a problem to get an optimization or mathematical model, you can use an existing solver to solve it. Let's say for solving LP, for solving many complex problems, we've already had very powerful model, existing model. But nobody's gonna help you model the problem. I don't believe even in 20 years, any algorithm or any machine can help you model the problem. Because if that is the case, then we'd better be careful. You know, that means the machines can really replace the position of human in society. If they can model a problem, that's, to be honest, that may not be good. That may be very terrible. That may mean the end of the life. So you still need to, you know, model the problem by yourself. In my personal view, modeling is one of them. I guess I can delete one of. I think it is the most important thing for operations research, for, let's say, undergrad level operations research. So you need to know the modeling tricks, and many examples can be found in lecture 1 and 8. And okay, so after it, we will have the graphical method for solving LP. This is in lecture 2. The graphical method for solving LP. And remember, for the graphical method, we have what? We have the feasible region, which is the intersection of all constraints. Okay. For the constraints, as we mentioned, first you'd better you'd better a bit bigger. No, cannot be in the middle. Say something like 60 something. Great. First of all, you need to write the slope. You need to write the slope of it. Anyway, first of all, you need to write the slope of it, which is here. And then after getting the slope, you just need to judge which, sorry, I'm talking about the objective function. You need to write the slope first, and then you need to judge which direction as the improving direction. Remember the trick to fix one variable to be 0, and you only need to see the other one. For example, you fix x to be 0, then you only need to see x2 direction, which makes your life much easier. And the target thing is that for a fixed feasible region, I want to move my line, for example, this line, this is the improving direction. I keep moving until the last point that I can touch the feasible region. And this point must be what? This point must be the optimal solution to my problem, LP, okay? So this is the graphical method. And after the same place in lecture 2, we have introduced the Excel solver. See here? I believe you have already practiced a lot, in examples. So this, I think, is very simple. Okay, then after it is one of the most important thing, which is simplex method. So we introduced it from lecture 3, lecture 4, and lecture 5, which are simplex methods 1, 2, 3. So in simplex method 1, which is in lecture 1, lecture 3, basically there are principles, ideas, and concepts, okay? Principles and concepts. Here we've mentioned the idea of the simplex method. Actually, we got insights from what? A 2D LP or from the graphical methods. And also we defined some theorems, and this is extremely important, the principal idea of the simplex method. And actually we're doing just two things, checking extreme points, and then C, optimality test, checking extreme points, optimality test. And here are some terms like the standard form of an LP, how to convert it to standard form. And here are about the basic variables, non-basic variables, degrees of freedom, this kind of concepts. And here are more properties of the adjacent extreme points and how to determine which one, how do you find an adjacent point of a given point. And then finally, again, is this idea. And now in lecture 4, we introduced what? The detailed calculations, okay? Calculating by simplex method. So first of all, you need to know how to start, how to operate the simplex method from a given point. So for example, here in most cases, we start from 0. Here we go, in this example. Why? Because if I start from 0, I directly have this. This is what? This is pivoted, see it? Because my x3, 4, 5 are selected as basic variables, and this is pivoted. However, I don't have to start from 0, okay? For example, here, I remember many students had a question here. As in one homework, I remember I asked you to start from another point. Let me find where's the homework. Homework number 2, I believe. Okay, so here I ask you to start at 3, 0. So what is the point here? The point is exactly the same as this. So this example. If I want to start from here, so okay. In this case, I'm gonna have what? I'm gonna have nodes. I'm gonna have x1, 2, and 4 to be my decision variable, to be my basic variables. x1, 2, and 4. They are my basic variables. And then you have a look at the columns of x1, 2, and 4. See what are these? They are not pivoted at all. See it? And for simplex method, I must start from a pivoted table. So that your very first thing to do is what? Is to pivot it. After pivoting it, you're gonna have this, and you can clearly see there's only one in each column and only one in each row as well. And the first row, the corresponding coefficients of the basic variables are zeros, and hence it's pivoted. And then you're gonna do the same, determining entering variable, determining leaving variable, and pivoting and optimality test, the same. Okay, so don't forget this. That is very important. And we also compared it with the graphical method. Where it is here. Here we go. It's right here. Remember, I have a summary. Okay, here we go. So initially, if we start from 0, so this is the result of course, my initialization, and this is the result of iteration 1, iteration 2, and iteration 3. And you can clearly see, actually, what simplex method was doing is exactly the same as the graphical method. And again, the principles of the simplex method. I check an extreme point to see whether any of its adjacent neighbors can improve me. If someone can improve me, go to that one. If cannot improve me, then I'm the best. If none of the adjacent neighbors can improve me, I'm the best. See here. So in simplex method, how would you determine it? You actually determine it by seeing the variables, the coefficients in the first row of a pivoted tableau. If everything is non-negative, then what do you have? Then you claim that this is the best solution. Regarding the reason why, I remember I showed you on the whiteboard at that time when we still had the face-to-face class lectures. Okay. However, if something is negative, then what? Then it's not optimal. I need to choose in the traditional rule, I need to choose the most negative coefficient, the corresponding column, to be my entering variable. For a branch rule, that's another story. I will always choose the one with the minimum index, the negative column with the minimum index. Okay, so here, that is how to operate the simplex method for a given point. This given point can be any, not necessarily 0. So you may need to pivot it. Very important. Okay, then after that, we mentioned something tricky about the simplex method. Here, mainly we discussed 4 cases, which are the unique optimal solution, which is here, unique optimal solution, multiple optimal solution, and unbounded LP, and finally is infeasible LP. Okay, in the infeasible LP, we mentioned what? The Big method, the formulations and the calculations. The Big method, what is the purpose? The purpose is to what? To find a start point and meanwhile solve the problem. If you cannot find a starting point, in other words, let's say finally there exists one artificial variable to be non-zero, then your LP is infeasible. Okay, so we introduced these 4 parts. Please review very carefully how to determine them. What are the determination rules? The decision. What are the detection rules for them? And you need to know how to operate the Big method. Okay. And after, in the same lecture, we also mentioned the degeneracy. So what does degeneracy mean? And we actually here we mentioned that the degeneracy is really, really bad. It makes the simplex method slower, and the worst case is that it may make the LP or the simplex algorithm to cycle, which is super bad. And how we can avoid it? We introduced the Bland's rule. The purpose is to avoid cycling in the simplex method. And by doing the Bland's rule, I can actually what? I can actually avoid the cycling. Okay, this is about LP degeneracy. Okay, then let me close all of them. Then after it, we had what? We had sensitivity analysis and the shallow price. It's too big. For the sensitivity analysis and the shallow price, the most important thing are what? Are the definition. What does sensitivity analysis mean and what does shallow price mean? So for the sensitivity analysis, we've introduced the two types of the calculations. First is a change on one coefficient of the objective function. See here. And the second case is one change in the right-hand side of a constraint. Okay, and you need to know how to operate it in the simplex method. Basically, actually, it's nothing but the optimality test, actually. Okay, if you're not clear, please review the lecture and also the homeworks. You need to review all the homework assignments carefully because problems could be something very similar from the homework assignments. Okay, and for the sensitivity analysis, for the shadow price, first of all, what is the definition of the shadow price? I actually forgot one thing here, which is here, the definition. And the second thing is the difference, the shadow price and sensitivity analysis. This is very important. You need to know the difference. They are talking about two different things, okay, which is right here, you can see. And one very important interpretation of the shadow price is what? As the marginal return here. Did I write here or here? Let me see. I think I wrote it here. This is actually the margin. The shadow price in economy is actually the margin. And then for the shadow price, you need to know how to read, very important, how to read instead of directly calculate, how to read the shadow price from the optimal simplex tableau of the original LP. And then later in the LP duality, we know this is actually nothing but a dual LP. But it is the same as the shadow price, okay? Then here, corresponding to the types, different types of an LP, you can read directly what is the shadow price by the coefficients in the optimal tableau of the original LP, okay? And here are some examples. And finally is the Excel. Keep in mind that because you're gonna take the exam at home, so it's very possible that I may ask you to use Excel to solve the problems. It's very possible. And then you're gonna submit, for example, your Excel file. You know, everything is gonna be electronic. That's good. That's gonna be very clear. Okay, so make sure you know how to operate Excel solver and also, for example, how to read the sensitivity analysis by Excel solver. Be careful here that I'm not gonna be satisfied to say you just give me this example, this tableau from the shadow price report, sensitivity report of Excel done. No, you need to interpret it because it's meaningless. You know, you just give me the number like this. I need to interpret. For example, what does this 0.5 mean? What does this 0.4 mean? You know what I mean? For example, I can ask you, for example, I can ask you this. For example, there's a change in the coefficient of x1. And I ask you to use Excel to solve how large is this change allowed. Okay, now you need to tell me this. So first of all, you need to show me this table, which is sensitivity analysis report. And the second thing, you need to tell me that, well, the allowed, see here, I'm talking about here. This is corresponding to x1, see it? The allowed increase of x1 coefficient is 4. Allowed decrease coefficient is 0.5. In other words, your delta should be between what? Between negative 0.5 and 4, positive 4. See it? Okay, that is the thing that you need to tell me. And again, sensitivity analysis means what? Means what is the range of the change such that the basis of the solution will not be changed, right? So you need to report to me this, okay, rather than just give me a tableau. It's not, you know, it's not enough. Okay. Okay, this is everything about sensitivity analysis and shadow price. And the final thing we introduced in the LP, is actually the LP duality. LP duality is here. Okay, so for the LP duality, first of all, is the definition of the LP duality. And by the definition, a very simple way, which is the two-step method. For the two-step method, what you're gonna do is first that you standardize any LP to be a standard LP. And then be careful, I'm talking about standard LP, not standard LP form, okay? Standard LP means for maximum problem, It should be everything is less than or equal to 0, the constraints sign. And the sign of all variables should be greater than or equal to 0. For a minimum problem, all constraint sign should be greater than or equal to 0. And the variable sign is again all greater than or equal to 0. Okay, so first of all, the two-step method to standardize it, and then use this definition directly convert to an LP, the dual LP. The problem is it's very slow. And the truth is that using this by the direct method, which is very important for the duality, LP duality, and I remember in the midterm exam, I already had the problem like this. What you need to do is to use the direct method, okay, to get what? To get the conclusion here, to directly write the dual LP. And I had many examples here, and be careful about this. The dual of a dual is the primal, as we just mentioned, okay? And then after it will be the strong and the weak duality theorem here. So what are the strong and the weak? What are the weak and the strong duality theorem? Okay, and by the weak and strong duality theorem, we have what? One very important thing is the strong duality theorem here, that we must know the optimal values are exactly the same. This is very, very important. And then the thing is, after it is how to read the optimal solution or optimal value from the dual LP from the optimal simplex tableau of the primal LP. And we've seen this is actually the same as what? The same as shadow price. See it? And you can directly read it instead of solving it. How to read the optimal value, by the way? By the strong duality, you're gonna see what? The optimal values must be exactly the same. Okay, so you just copy the optimal value of the optimal value of the primal LP, then you directly get it. For example, consider this. This is the optimal tableau, right? And the optimal value of the dual LP must be -2. Done. Simple, right? Okay, so after the last thing about the LP duality is complementary slackness. We have two conclusions. Conclusion number one is that if X is not optimal, then Y is not infeasible, not feasible. If X is optimal, then Y is complementary optimal. And the second thing is the complementary slackness theorem that is corresponding to the slack variables. We have an if and only if condition, okay? Basically, these two things are the same because one uses the language of XY, the other one uses the language of the corresponding slack variables. So they're actually the same. So this is everything about the LP duality. Close it, close it. And after it are the things you guys, I think, are relatively more familiar with because we just finished it, the first thing is the dynamic programming, the DP. So first of all, the DP, what are the characteristics of the DP or the properties of DP that we can divide these problems to be stages and we have a recursive reformulation, okay? And then we use we use Dijkstra's algorithm to solve the shortest path problem, which is actually a DP. DP means dynamic programming, which is actually a special case of DP, or which is actually a DP algorithm. After it, we use the DP to solve what? To solve the unbounded knapsack problem. Remember it, which is here. No, which is here after it. Yes. What is an unbounded knapsack problem and how to formulate it? And finally, we solve it. Okay. So these are the things about DP. And after it, by the way, here are some interesting applications. For example, remember this example in your homework. I don't know how many of you tried this problem. I remember I listed as a bonus problem here. Let me see here, which is a maze. Okay, this is my solution, of course. I'm not gonna show you solution 6 again. The homework is due next Friday. Don't forget it. So the bonus problem is how to solve a dual in general. So how to solve a maze problem in general for any maze problem. So theoretically, you can just define it as different nodes and consider it as a SPP shortest path problem and done. Very, very simple, actually. Okay, so I remember when I was a kid, this kind of adults, they always give me this kind of maze problem to solve, and at that time I didn't know. I just thought that if I was smart enough, I can find, you know what I mean? Find, instead of find a general way, I can just, use my eyes to find. And later I realized if the graph is really, really big, it's impossible to use your eyes. So what is a systematic way to solve it? Here we go, shortest path problem. Okay, and after it will be lecture, which is lecture 10, which is the formulations about SPP, which is here, which actually here is already done network optimization 1. The formulations on SPP and also the applications of it in terms of, let's say, decision making here. Okay, and after it is what? The minimum spanning tree. For the minimum spanning tree, what is the definition of a tree? What is the definition of a spanning tree and minimum spanning tree? And after it, how to calculate the minimum spanning tree of a given graph. We've introduced Prim's algorithm and also Kruskal's algorithm. Okay, make sure you know how to use it, and because there's a time limit, so you'd better solve it relatively quick. Okay, then after it will be what? Will be, let's say, lecture 12, which is something that we just finished, which is the maximum flow and the minimum cut problem. The very first thing is the definition of maximum flow and how to formulate the maximum flow problem and what are the corresponding applications for the maximum flow. Maximum flow is actually much easier than the minimum cut problem. After it is the minimum cut problem. What is the definition of a cut? And for example, here we have different examples of cuts, but be careful here, they are not cuts because they are not SP partitions, okay? And how to formulate the minimum cut problem here. And we have introduced for both maximum flow and minimum cut problem, remember, we've introduced 2 groups of the formulations. And finally is the thing that we just mentioned, that the maximum flow minimum cut problem, which is MFB2 and MCP2 are dual LP problems. You need to be able to recognize this, and maybe I will ask you some problems, for example, to really explicitly formulate the problem. Okay, so I think that's everything about the review part. Any questions about the review part itself?
Yeah, how many questions are going to be on the final?
Good question. I haven't determined yet, but the time will be 2 hours. So for the final exam, what I'm gonna do is let me go. What is this? Okay, let me go to NDSU. I will write you several emails regarding the details about the final exams or something. Don't worry. But let me give you a very basic introduction here, because I realize not too many people are in the lectures. If for example now only 8, including myself, only 8 participants. If let's say academic schedule, if I just notify it like this way, many students may complain later, and I want everybody to know it. Okay, so let's see. This is 20 to 21, right? 20 to 21. Okay, so no. This is still 20. Let's see, 19 to 20. So we're here. So the very last. No. This is not what I'm looking for. Sorry, I'm looking for not schedule, but the final exam. Final exam schedule. Okay, so for the final exam schedule, come on, where it is? Okay, it's here. You can see that we're here. So the final exam is gonna be, it's pretty long, right? next week. The final exam is gonna be next week. So we're here, it's gonna be here. I'm not gonna change the date. So it's gonna be for 2 hours from 8 to from 8, that's really early. Okay, from 8 to 10. Not by me, by NDSU. Sorry about that, but that's the rule we need to follow. However, I know this time is a very special case, coronavirus. What I'm gonna do is that I want to have a kind of like a mimic, let's say, submission rather than exam. It's a mimic submission, kind of like a fake submission, not a real thing. I'm gonna make it something like you can see find from your assignments there in the BB. I'm gonna set up the same time, let's say from 8 o'clock to 10 o'clock, and you can submit something there. The purpose is to let you be familiar about the submission process. Trust me, although you have already had submitted many homeworks, but for the final exam, that might be something really new. So I will upload whatever problems, and to be honest, I will not really grade it. You can write whatever you want, but make sure that every problem is in 1 or 2 pages, and then after you can, for example, take the pictures about what you just wrote, make sure the picture quality is very good, and then upload it to the exam window or the slot in the BB, so that this gonna help you to get more comfortable when you're gonna really do it in the final exam on 15th. Okay, so we will do this, and I will write you detailed emails, an email about the detailed things, for this part, for this exam, and also we're gonna do what? We're gonna have some extra office hours before the final exam. I promise you, as I did, in the midterm exam. So yes, that's everything about the exam. Any questions? And also don't forget to check these kind of solutions are here, okay? Because I heard one student complain before that he said, oh, this guy never uploaded the solutions. Sorry, I don't accept this complaint. I actually mentioned it in the very first class, but maybe some people didn't see the solutions there, or they didn't want to see the solution. Then I have no choice. Any other questions? No question? Okay, that's everything about this semester. Thank you very much, especially under this coronavirus, the special case, for this class. And please wait for my emails about the further notifications. So next week, we will not have classes. Okay, everything I will notify by the emails. Thank you very much. And you have a good day. Thank you. Bye-bye.